My name is Jeff Reinemann. I've worked on Intel's real-time operating system. I've worked on the BIOS for motherboards. I've worked on system-level software, and I've done system-level performance analysis. And now I'm a technical consulting engineer in the software services group supporting Intel System Studio. And today I want to talk about IoT device performance and power optimization using Intel System Studio. So our agenda, I'll give a brief overview of Intel System Studio, and then I will discuss Intel VTune Amplifier, which is the performance analyzer, and then the Intel Energy Analysis tool, which is the power analyzer, and we'll have some time for question and answer at the end. So first of all, System Studio. With all the different devices in the embedded space, including IoT devices, transportation, retail, imaging devices, systems are getting more complex, more powerful, and solutions are networked and connected, and there's lots of complexity in these devices these days. So to address the complexity, to make your solutions more reliable and optimize performance on them, you need a comprehensive and easy-to-use tool set to help analyze the current solution. Something that will help quickly resolve defects in your systems and offer insight into your source as far as where your performance issues are and where your energy consumption issues are. So Intel System Studio is such a tool suite. It consists of compilers and libraries, analyzers, and debuggers. So the debuggers are intended for initial system bring-up, system-level debuggers, where it can interact with the system, or has a debug trace model where it can actually trace the execution of your system during system bring-up. And then you can examine what sequence of steps it took and why. And then when you're generating your solution, the System Studio offers C and C++ compiler and highly optimized performance libraries for imaging, signal, math, and data processing. And then to analyze and tune your solution, there are memory and threading utilities that will help analyze invalid memory access and memory bandwidth issues, and power and performance analyzers. And the power and performance analyzers is what we're going to focus on today. So the Intel System Studio comes in 3 different flavors. There's a Composer Edition, which consists of primarily the compiler and the optimized libraries. There's also Professional Edition, which includes the analyzers for performance tuning of performance, energy tuning, and graphics analysis. And an Ultimate Edition, which includes the application debugger, system-level debugger, and supports JTAG type interfaces over USB or JTAG connector. If you want to know more about these other components that are in the Intel System Studio, Richard Atwood gave a presentation yesterday entitled Intel System Studio for IoT Developers when he gave a brief overview into each of the different components. What we want to do today is do a deep dive into the VTune Amplifier for systems and the Intel Energy Analysis. So first of all, one example of a success story of a customer for Intel System Studio. They were developing digital surveillance video recording solutions, and their requirements were to support multiple channels of video data with varying resolutions. So VTune has 2 ways to collect data. As I mentioned, there's a software collector and a hardware collector. Software collector uses operating system interrupts and tracks the instruction pointer and call stack. And it collects this information from a single process tree. It has a 10 millisecond resolution. The hardware collector, on the other hand, uses the performance monitoring unit built into the CPU. And it has a 1 millisecond default resolution, so it's capable of a much finer granularity and can find issues with smaller functions. And it can collect data from the entire system or from the single process tree. The hardware collector, however, requires a driver to be installed in the system, whereas the software collector does not. The software collector collects basic hotspots. So this is essentially information on which functions consume the most time, the most processor time. It can also track concurrency issues to map the parallelism, so you can identify which processes are running across which cores, and it can identify locks and wait issues for transitions. The hardware collector, on the other hand, collects advanced hotspot information, which includes, in addition to the basic hotspot information, it includes statistical call counts. And that, again, is useful for identifying function calls that could be inline to improve performance. There also is a general exploration mode where you can do analysis into additional architectural issues, such as cache misses and branch miss predictions. And then there are deep dive analysis to analyze things like memory access analysis or storage analysis to try and tune for bandwidth and other access contention issues. So now that we've collected the data, how do we use VTune to find the information that we're looking for? So when VTune is done collecting the data and presents the initial results to the user, it starts out in a summary tab. So we see that at the top, we have elapsed time, and the elapsed time is essentially the wall time, the clock time that it took to execute the program. Beneath that, it presents information on hotspots and finally a CPU utilization histogram. So the x-axis on the CPU usage histogram is basically 0, 1, 2, 3, and 4. So we have a 4-core system here. So it's the amount of time that the solution was utilizing the different cores in the platform. So in this case, we see that the majority of time, our application was utilizing either 3 or 4 cores, which is pretty good. If we go back and look at elapsed time, the CPU time number there is the summary of the execution time on all of the cores. And the instructions retired are presented here. And we see that VTune has the ability to flag parameters or values that it thinks provide an opportunity for optimization. In this case, the cycles per instruction with a 4-core system, there theoretically could be 4 instructions retired for every cycle. In practice, this is very difficult to achieve because there will be stalls for fetching memory, loading the cache, and branch miss prediction. So in general, a CPI rate of 1 is considered good. In this case, we have a CPI rate of 7.5, so there will be opportunities as we analyze the data deeper to identify places where we can better optimize memory access or cache utilization. In the middle here, we see the top hotspots where our application is spending the majority of its time. In this example, the multiply 1 function is executing for 210 seconds of the entire 212.5 seconds of execution time. So that is going to be our primary place to look for optimization opportunities, because we can optimize, any place else we optimize is not going to have near the improvement time-wise, execution times. After looking at the summary, we want to look at the bottom-up view, and this provides a visual of how much time each function, in this case, executed. If we look at the top window, we have an option for grouping by either function and call stack, or module, or thread function and call stack. In this case, we're looking at the function and call stack, and it's highlighting which functions are taking the majority of time. In pink, under overhead and spin time, it highlights opportunities that it believes are the greatest opportunity for performance improvement. There is also a system call stack subwindow here, which is displaying the call stack for the selected function over in the function and call stack subwindow. And that can also be demonstrated over there by expanding the function and calls over there. At the bottom, we have a timeline which shows us the execution of the, in this case, we're looking at threads. We're looking at the application execution across the different cores and the thread execution. It tells us the overall CPU utilization. There are filters on this where we can filter by process or thread or module to zoom into the data that we want to look at. And if we double click on our module, we then expand into a view of the source. And it will take us right to the source code where that module is spending a lot of time with the lines of the source code. And we see a heat map in the middle here, so we can zoom in on all the different locations in our source code with the scroll bar to identify that. And associated with the source code, it shows us a relative CPU execution time. And when we highlight and select a line of source code, we have the option of looking at the assembly language associated with that source code, and it will show us a highlighted portion that maps to that individual instruction. So this is a very powerful way to go and identify exactly which line of code is causing issues, and making sure that if you're using, for example, SIMD or vectorized instructions, that they're being properly utilized in the assembly. The thread behavior here shows you the utilization of the different threads and cores, with the brown color in this case showing you actual CPU utilization. So we can see on the left, at times there are very good utilization across the cores, and on the right it has a lot lower utilization. And you can select and zoom into different subsets of the timeline to actually see what's going on in those cases. There is also a locks and waits view where you can view transitions. This is essentially where one process or thread is waiting on another thread to release a mutex or semaphore of some kind, a lock or wait. And every time that a lock is released and there's a context switch, because of that, it identifies it here. So if we see an excessive number of transitions, that indicates there may be an opportunity to improve parallelization of the algorithm. And now I'd like to go into some of the workflow that VTune enables. So VTune supports a command line execution. The path to find it for Windows or Linux environment is listed here. And the user interface also provides a command line button, which will generate the command line to execute on the target system with the proper parameters for the data collection configuration as you specify in the user interface. And then after executing on the target system, it can be imported back into VTune for visualization and analysis. VTune also enables remote data collection. So you can configure an SSH into a remote Linux target. We can configure it to launch either attached to a process, profile the entire system, or to launch a specific application with parameters. And VTune will use that SSH to execute the command remotely on the target system, collect the data, import it back into VTune and show you the results in a visual user interface. VTune also has a compare capability where it can compare the results of different runs. So as you're optimizing your code, you can see what has changed from the performance perspective, so you know what is improving your performance and what is not. Or you could use it to compare different algorithms, or you could use it to compare the same algorithm on different systems. So an example here, this is comparing two different executions, and it's showing you the difference where one execution took 143 seconds and the other execution took 28 seconds. And it tells you the difference between the two, and it breaks it down across all the data points that it's collecting. And it also shows you the difference in hotspots across the different executions. And for example here, in this case, it's comparing two different algorithms, one called multiply one called multiply two, and showing that that is the primary difference between the two executions. And the CPU histogram also shows you how the core utilization has improved from one algorithm to the next, where in this case, the first algorithm was primarily executing in only 1 or 2 cores at a time, and the second algorithm being compared was primarily executing on 3 or 4 cores simultaneously. So in summary, Intel VTune Amplifier enables you to improve the performance of your scalable code by helping collect all the relevant data you need for analysis. Visually helps you zoom in onto the areas you need to focus on so you can find answers fast, and it's easy to use. So Intel System Studio and its VTune Amplifier component provide accurate profiling data with low overhead to provide an opportunity to do advanced performance optimization. Now I'd like to transition into looking at the Intel Energy Analysis tool for energy profiling. So the Intel Energy Analysis component allows you to optimize your code, which is targeted for devices that are executing on battery. And this is important for extending the battery life of the system and finding behaviors in the code and the system solution that waste energy. For example, some of the ways it does this is it maps interrupts to the device that's generating the interrupt and timers to the scheduling or process to demonstrate what type of events are causing the system to wake up and consume energy. This is available for Windows 8.1 and later, Android, and Linux. So there are two components to the Intel Energy Analysis tool. There is a collector and there is a visualizer. The collector is called SockWatch. So it's a command line tools that collects platform power relevant metrics. It collects things like C states, P states, ACPI states, and different power events. And then once you have that data, you can either look at it in the CSV format that the collector presents, or you can import it into the visualizer, which is actually a component of VTune, and that will give you a graphical representation of the data that you're looking at. So first of all, a brief description of what the different P states and C states are and why they're important. And this is just an example. Every processor is going to have a different number of P states and different number of C states. So this is just one example. The P states are the frequency that the processor is running at. So P0 is going to be the highest frequency, which is also going to be consuming the most amount of power. The PN represents the lowest frequency that processor is capable of running. And the reason that the system would be changing frequencies would be to adjust the power consumption and the performance needs and balance those out. So the C states are the power states for the core. C0 is the active state, and anytime you're in C0, then the P state is going to be executed. The higher the C state number, the deeper sleep that core will go into. However, the deeper the sleep, the more power savings you have, but the more expensive it is to come back out into the C0 execution state. So you don't want to have lots of transitions into the deepest C states and then back again. So there will be an opportunity to take a look at the algorithm to optimize what is a proper C state to go into. So as mentioned, the SockWatch data collector can capture all of the C and P states for both the CPU and GPU and different device states and packaging temperatures. There's no external hardware necessary for this data collection, and it's very low overhead. And it outputs detailed reports in text CSV format, and it's capable of reformatting the output so it can be imported into the VTune amplifier for visual representation. So this is an example of the CSV text files that are produced by SockWatch. You get summaries on things such as the CPU C state and the core residency, energy consumption across the different packages, and device states. When that information is exported into a format that can then be imported into the VTune visualizer, the Intel Energy Analysis visualizer, you get a summary view, which will show you similar things to what VTune collected, such as elapsed time. It'll also tell you items, data such as your wake-ups per core, your frequency histogram, and your top causes of core wake-up from C states to C0. It also displays this information in both table format or in histogram format, depending on how you want to view it. So we can see, for example, here, in this particular case, the majority of the time was in C0 state, and when it was in C0 state, the majority of that time was spent at 2.7 gigahertz, which was pretty close to the maximum frequency. So this data was collected while the system was probably pretty busy. The energy analysis visualizer can also show you a timeline and show you different C states for the cores across time. So it can allow you to, and you can select subsets of the timeline, so you can zoom in on specifics. And as you zoom in on those timeline areas, it can also show you what caused that transition, what the event was that caused the wake. So here's a little bit more example of when you're looking at the summary view, looking at the C states, it can show you by, in this case, by package, which is the die. It can show you by the core on the die, the distribution of your C states. Or it can show you by the thread in a hyper-threading solution. And it can also show you wake-up events across the cores and threads in both histogram and table format. And similarly, the graphics C states you can view by table or histogram. there is a tab to show you, to zoom in on the thread C states and be able to provide that information, showing you the utilization of the different threads on the different cores. And it can correlate the data across threads in both the CPU and GPU, and simultaneously show you the thermal measurements for that processor. So it's a very powerful tool to help you map power transitions and heat dissipation and thermals. So to summarize Intel energy analysis, it helps to optimize your software and system solution to extend the battery life of the device hosting your solution by providing you data that is useful to reduce and consolidate wake-up events, and therefore save energy by staying in your low power state longer and reduce the number of transitions from low power states to active states. So together, Intel VTune Amplifier and Intel Energy Analysis provide easy to use, powerful analyzer tools that give you relevant data to be able to zoom in and optimize your both performance and power efficiency in your IoT solutions. And I have some product information here. There's a website for Intel System Studio if you want to try it and download it. There is a beta program for Intel System Studio 2018 going on right now that you can participate in, and additional information up on the website about Intel System Studio. As I mentioned earlier, there were several other presentations that cover different aspects of Intel System Studio. Richard Atwater provided one that gave a general overview of all the different components, and Chakingam provided a deep dive into the performance libraries and how to optimize for IoT solutions, specifically for some automotive use cases. So thank you very much for your time.